Hi, this is Project 206, Ball Bounce Efficiency by Paige, Courtice, and Alexandra. So our research question we developed for this project was motivated by the fact that summer's coming up very soon. We both really like to play tennis and basketball in the summer, but we also know that these sports can be kind of intensive. We wanted to make sure that we are able to conserve energy as best as possible, and we were wondering if it would be more efficient to stay low to the ground when bouncing balls, or would staying up high result in higher bounce heights, allowing us to expend less energy to meet the ball where it ends after its bounce. Alternatively, would it just be easier to stay inside and play ping pong? So basically our research question is, how does drop height affect bounce efficiency, and how does bounce efficiency change when different types of balls are used? In order to measure bounce efficiency, we had to calculate two potential energies. So we calculated the potential energy at initial drop height of the ball, as well as the potential energy at the average bounce height of the ball. We calculated efficiency by dividing the potential energy at the bounce height by the potential energy at the initial drop height.
To answer our research question, we used three types of balls: a basketball, tennis ball, and a ping pong ball. Each ball was weighed to determine their respective masses so that their gravitational potential energies could be calculated. We marked each ball with a pen to ensure that we dropped it in the same configuration each time in order to minimize uncertainty. We made markings on a wall in 1 centimeter intervals, making a bolded line every 5 centimeters for ease of bounce height observation. We dropped the balls from 3 predetermined heights: 1 meter, 1.5 meters, and 2 meters. Each ball was dropped 5 times from each of the 3 heights for a total of 45 drops. We dropped the balls with the height marker at the bottom of the ball, and the bounce height was determined by the line where the bottom of the ball reached. We were able to observe the bounce height by taking a video on an iPhone for each trial. We then replayed the video and paused it when the ball had reached its peak bounce height, which was when the ball was no longer seen as a blur. We then compiled the data for each bounce height on Excel.
In order to minimize our uncertainties, we made sure to designate each of the roles. So we made sure the ball was dropped by the same person in each trial, and the video was recorded by the other person. Also, recording of the drop was rewatched by both experimenters. We then both came to a consensus on what the peak bounce height was. Finally, each ball was marked to ensure it was dropped with the same configuration in each trial. This is our results. So this is the results for the basketball, and we can see at 1 meter, the average drop height was 0.634 meters. At 1.5 meters, it was 0.936 meters, and at 2 meters, it was 1.18 meters. We can also see that the efficiency at 1 meter was 0.634, at 1.5 it was 0.624, and at 2 meters it was 0.59. This is our data for the tennis ball, and we can see that at 1 meter the average bounce height was 0.624 meters, at 1.5 meters it was 0.856 meters, and at 2 meters it was 1.04 meters. The efficiency at 1 meter was 0.624, the efficiency at 1.5 meters was 0.571, and at 2 meters it was 0.52. Finally, this is our data for the ping pong ball, and we can see that the average bounce height was 0.698 meters at 1 meter. At the height of 1.5 meters, it was 0.87 meters, and at 2 meters, it was 1.012 meters. The efficiency at 1 meter was 0.698, at 1.5 it was 0.58, and at 2 meters it was 0.506.
To analyze our data, we carried out the calculations described earlier. The potential energy for each initial drop height was calculated, as well as the potential energy for the average bounce heights. Bounce efficiency was then calculated using the equation efficiency equals potential energy of bounce height divided by the potential energy of the drop height. These efficiencies were then compared to answer our research questions. We measured uncertainty using standard error and showed these as standard error bars on our efficiency versus drop height scatter plot. The error bars were quite small, indicating little uncertainty in our experiment. Overall, we found that as drop height increases, bounce height also increases. However, bounce height efficiency seemed to drop slightly as drop height increased. In terms of the effect of ball type on efficiency, we found that the ping pong ball had the highest bounce efficiency at 1 meter, while the basketball had the highest bounce efficiency at both 1.5 meters and 2 meters. That being said, on average, the basketball had the highest bounce efficiency at 0.616, and the tennis ball had the lowest bounce efficiency at 0.5 0.71. In conclusion, differences in efficiencies were fairly minimal, but we could conserve more energy if we bounced any of the balls from a lower height. If heat stress is a concern, it would be best to stay inside and play ping pong. But if heat stress is less of a concern, playing basketball would be the more energy efficient sport to play over tennis. Thanks for listening!